So, time to move on to our next topic, 7.12, which concerns variation in populations, specifically genetic variation in populations, and how that can adversely or you know help a population survive. In this case, we're looking at the California condor right here, right? Kind of you might think it's kind of an ugly bird, but it's kind of one of the largest. I think it might have the largest wingspan in North America. And I happen to think it's kind of cute. That's just me. So they experience what's called, and you've seen this word before for sure, but a genetic bottleneck, right? Which, when that happens, if you remember, pretend that you have a bottle, right? You have all these genes that are shuffled up in here, right? All these different genes for many different things, and you have an event in which this population is reduced to just a few individuals. Now, once that happens, this leads to lower diversity. Lower diversity genetically, right? There's less genetic variation. Lower diversity, lower genetic variation. Genetic variation. Well, this has an effect on survivability. The lower the diversity, lower the genetic variation, the greater the chance that species will go extinct. Greater chance of extinction, and a greater chance of not surviving. Greater chance of extinction. Because, as it might make sense to you, the less diversity you have, if something comes and affects this population, it's more liable to wipe them all out, right? And you'll see in this summary here, it says that the existing genetic diversity of condors, all of which are descended from 14 individuals. This is a population bottleneck, right? These 14 individuals. There are 14 individuals surviving that. That's a bottleneck. This paper says that they were more genetically diverse, but they had a huge crash. Again, a lot of this is due to human activity in the area, moving into the area. So this led to a greater extinction possibility because of the low genetic variation, low diversity, greater chance of extinction, the lower chance of survival as a species. So the reverse of this, if you look at this little guy, this cute guy, it's a cockroach. Nobody likes cockroaches, I know, but one of the reasons, I know you've heard this before, like cockroaches will be around long after us. They can survive anything. The reason for this, as they're finding out, is they have a high degree of plasticity, which means that they can develop very differently based on environmental pressures. They have a high amount of genetic diversity. They have a super high, large genome for their size. I think they have about, it says over here, maybe it doesn't say here. They have about 20,000 proteins that their DNA can make. So they have a high amount of genetic diversity. Genetic diversity, variation. Right? This is going to lead to increased survivability or a lower chance of extinction, right? Sorry. Lower chance of extinction. Right? Variation is huge for helping populations survive in the wild. And you'll notice this. It's incredibly hard to get rid of these guys. You almost just can't leave food out because they're going to find a way to come back no matter what type of pesticides you throw at them. So they have a huge amount of genetic variation, huge amount of genetic diversity. They can make many different types of proteins. They are very resilient to anything you're going to throw at them. So they have a much lower chance of going extinct and a much higher chance of surviving for a long, long time. So this is just, I wanted to kind of touch base a little bit about variation, which stems from, I'll just point this out too, where does variation stem from? Ask yourself that question. Mutation. Just keep that in mind. Side note there. Variation stems from mutation. This existing variation in populations gives rise to much higher resiliency as a species. And that's it.